If you throw two tennis balls so that their paths cross, they either miss each other or collide and bounce apart. Particles simply cannot occupy the same space at the same time. Waves, however, behave entirely differently. When two waves meet, they pass directly through one another. As they overlap, their individual displacements combine to create a single temporary resultant wave. This is superposition. In this unit, we will take the abstract mathematics of wave phase and use it to explain the real world, the noise-canceling technology in your headphones, the vibrant colors seen in soap bubbles, and how physicists measure atomic spectra. Everything in this unit starts with one rigid, fundamental rule. The principle of superposition states that when two or more waves meet at a point, the resultant displacement is the algebraic sum of the individual displacements. You will learn to apply this rule to graphically add wave pulses together, predicting exactly what the medium looks like at the exact moment of overlap. When continuous, coherent waves overlap, they create stable, geometric patterns of interference. If they arrive in phase, they construct to make bright light or loud sound. If they arrive out of phase, they destroy each other, leaving darkness or silence. You will master Young's double-slit experiment, using this classic equation to link the wavelength of light to the physical geometry of the slits and the resulting interference fringes on a screen. Next, we explore diffraction. Why do waves spread out when they pass through a narrow gap or around an obstacle? You will learn why this spreading effect is the ultimate proof that light travels as a wave. We will examine the unique intensity pattern produced by a single slit, and you will learn to predict exactly how that pattern changes when you alter either the wavelength of the light or the physical width of the slit. We then scale this concept up dramatically. By using thousands of parallel slits, a diffraction grating splits white light into its component wavelengths with extreme precision. You will use the diffraction grating equation to calculate the maximum number of observable orders. More importantly, you will practice the crucial exam skill of converting grating labels, usually given in lines per millimeter, into the grating spacing in meters. Finally, what happens when two identical waves travel in opposite directions? They trap energy in fixed oscillating patterns known as stationary waves. You will learn to identify points of zero movement, called nodes, and points of maximum amplitude, called antinodes. By understanding that the distance between adjacent nodes is exactly half a wavelength, you will solve complex practical problems involving guitar strings and resonance in air columns. Superposition is a high-yield topic that tests your ability to visualize geometry and manipulate algebraic formulas. By mastering these 5 topics, you will unlock the physics behind all wave interactions. You are now ready to begin Topic 1 and learn exactly how to calculate the resultant wave when two individual waves occupy the same space.